Hello, all. This is the review recording for the second exam. Uh, I'll put this in the email when I send this after I convert it to a YouTube. Uh, I'm anticipating giving this exam on the Wednesday that we return as opposed to the Friday. And if there's strong feelings about that, you have to let me know by email. So, I'm not going. I'll be around. I'll have my computer wherever I travel over this vacation period. So if you get to it, then just shoot me a message, and we'll go from there and see what happens. Everything on Monday. All right. With no further ado, here we go. So it's just me narrating, obviously no pictures, and I'm going to let me get over here. So sorry. I'll get this started. I'll have to take a look at the exam. So here I am coming from the exam. So there's two sections that are there. We're dealing with autonomic nervous system and we're dealing with endocrine. Those are the two big players in this. I mean, they're about. I think the questions are about equally divided. There's 50. It's just two chapters. Right now, you have that take-home test that's dealing with that effectively is a lab exam on this. And when we come back, the third exam undoubtedly will feature the immune system and blood pressure. I think are the major topics in that, possibly respiratory. We will see. But nevertheless, here we go. Endocrine. What's an endocrine hormone? Goes directly into the bloodstream. Doesn't have, they're by definition ductless glands. That's the distinction between exocrine and endocrine. By and large, they're proteins, though there are a limited number that are fat. So they're peptides and proteins or protein based, with a limited number that are not, principally made from cholesterol. Okay. The glandular structures are relatively small, and that's really the discussion. So it's a very unimposing anatomical system. It's a very massive physiological system. So again, mostly proteins, mostly small glandular structures directly into the bloodstream, absence of ducts, etc., etc. Those are all things, and they control. Really, they're your second most important control system, if you will. Important might be the wrong term. Second most rapid control system as opposed to the nervous system. So the ones that are not peptide or amino acid based are based in what? The common denominator of that is they're called steroidal hormones. So they're derived from our principal steroid compound, cholesterol. Okay, you're all familiar with that, I'm sure. So cholesterol based, they have the luxury of making their way rapidly through membranes, as opposed to ones that are peptide based, which do not, which have to utilize receptors on the external aspect of the cells or the cells that they have where the receptors appear, since there is a variation in target cells, depending on the hormone that is part of the deal, so to speak. The oddball again is thyroid hormone because you're dealing effectively with two uh, symmetrical symmetrically placed tyrosines, and you add either three or four iodines to them. It's the symmetrical nature, that sort of anti-parallel arrangement. One's right side up, one's upside down, that create this interesting molecule, which is relatively small and easily fat soluble, so it can travel through membranes as well. So it's sort of the oddball in the midst of all the other peptide based hormones, even though that's still its classification. It's just the chemical symmetry that impacts it more than anything else. It's an interesting molecule with certainly very, very widespread effects. And that really underscores what endocrine is about. Some of these have very limited targets, and some of these have full range targets. Growth hormone, thyroid hormone, all over. Nearly every cell has receptors for that. Insulin, nearly every cell has receptors for that. I mean, you struggle to think of ones that do not have it, or unless it just physically can't get there. I mean, these are so there's really a very, very interesting uh, system, and to me, just one that is almost a course unto itself when you really get into the diseases. And the one I'm speaking of mostly is diabetes, for anything else. So if they're water soluble, and the way I describe it would be water or lipid soluble, I think that would be the easiest way. Water soluble ones, G protein receptors, have to utilize second messengers like calcium or cyclic AMP, the standard G protein pathways you've already seen 100 different times. All of that's really important. Okay, that's there. Where the lipid soluble ones, they typically they pass directly through the cell membrane. They bond and complex with receptors in the cytoplasm. That's the vast majority. Then that combination of that complex of receptor and lipid soluble agent or hormone, then are able to pass through the nuclear membrane and exact their action or manifest their action by way of transcription and translation, as they effectively impact DNA directly. Yes, there are probably a couple of these that go right into the cytoplasm and then right into the nucleoplasm and find the receptors there. I can't tell you which ones they are, but in general, the vast number of them in the cytoplasm is where we find this more than anywhere else, and certainly not on any kind of a membrane whatsoever. Okay. And it works on ribosomes, and it works on ribosomes indirectly by way of impacting transcription and translation. So I think that's all important as well. Okay. So the other major system was certainly the other chapter was the autonomic nervous system, and really they're intertwined because there's overrides. For instance, in override, the autonomic nervous system has the ability to override what's going on in the endocrine system on a short-term basis, and the best example of that by far and away is fight or flight. I mean, that really is where it's all about, because not only do you get a variety of actions that are designed effectively for survival or emergency basis, but you get this prolonged, relatively speaking, uh, chemical imbalance by the release from the adrenal medulla, which is really nothing more than a misplaced ganglion of the sympathetic nervous system, and it releases directly into the bloodstream via an endocrine action, epinephrine and norepinephrine, and they really are the ones that prolong the impact, because things that are released, the endocrine, even though it's a nervous system, this sort of, and I hate to use the term endocrine, I'd say endocrine-like arm of that system really prolongs its activity. You've got to know who the hormones are, where they come from. We start with the posterior pituitary. Basically, it has two major named hormones that everybody needs to be familiar with: oxytocin and antidiuretic hormone, also known as vasopressin. Any of those names are fair game. You should know what they do. Effectively, they're a neurotransmitter that are released directly by the posterior pituitary directly into the bloodstream and function as a hormone. Their target is remote comparatively, but specific. I mean, oxytocin, principally specific target on receptors in the birth canal to facilitate smooth muscle contractions. Remember, it's a positive feedback loop. And vasopressin, very, very specific on the kidney. We've seen the anatomy. We'll get to the physiology. It principally works in collecting ducts and distal convoluted tubules and facilitates the reabsorption of water so it doesn't get urinated out, hence anti-diuretic. It opposes diuresis or urination. The other thing, and this is the ones that people forget, there are both we call RHs and IHs, releasing hormones and inhibiting hormones. Not for every single structure in the pituitary, not for all the different hormones that the anterior pituitary releases, but many. I mean, the one that you'll hear the most about over time, particularly when you get to repro, is GnRH. That's gonadotropin releasing hormones. So releasing hormones are an up regulator, inhibiting hormones are a down regulator in the sense that releasing hormones induce the pituitary to release, let's say, growth hormone. And inhibiting would be to impede or at least limit the release, let's say, of growth hormone or thyroid hormone or whatever it's inhibiting. So don't forget those. Those are all coming from the posterior pituitary. The anterior pituitary, what I always refer to as the big six: growth hormone, HGH, ACTH, adrenocorticotropic hormone, TSH, thyroid stimulating hormone, not to be confused with thyroid hormone. This is just to trigger the thyroid stimulating hormone goes directly to the thyroid and says, "I need more hormone to be made. We're running low in the bloodstream." Right? Again, most of these are, with limited exceptions, all negative feedback loops. The big one, of course, being the oxytocin. At least for our purposes now, we're going to see some of them in repro, but we'll focus on the specifics in repro physiology toward the end of the term. And so, with those out of the way, the TSH, the ACTH, and the HGH, we have the last three are all reproductively oriented. Follicle stimulating hormone is about stimulating the follicles, and principally that means eggs and sperm. Luteinizing hormone is stimulating other cells in the area, in the area of the reproductive structures to produce estrogen and progesterone in the female predominantly, and testosterone in the male. Okay. And then lastly, I have prolactin, and other than its role in lactation, and certainly being increased amounts of it in, let's say, both lactation, and it certainly plays a role, though it's not a clear role with regard to reproductive function in the female. What it does in the male is totally unclear. And that's always been the one we've known the least about. The interesting thing is, it's just the quirk, and I think quirk's the wrong term when you start describing tumors, is that when we see pituitary tumor, and pituitary tumors are much more likely to occur in the anterior than the posterior. Posterior is nerve tissue, not that prone to tumors. The anterior pituitary is glandular tissue. Very glandular tissues, what we call adenomas or adenocarcinomas, particularly are effectively clusters of lining tissue. And I mean, unfortunately, there's a fairly goodly amount of these that occur. And when we see this evidence, one of the tells, one of the giveaways, is inappropriate lactation in a female who shouldn't be lactating, or certainly in a male at any time shouldn't be lactating. So all of that's something that's worth remembering as well. So I think that's important, and all of those different hormones and exactly where they're produced. So that's really what it's about. So know those six and know the targets. I mean, again, HGH, very widespread. ACTH and TSH, very limited. It's either the adrenal cortex and adrenal corticotropic hormone, and the thyroid and thyroid stimulating hormone. And the reproductive structures I've already given you. Okay. So you have to know the range of cells that they each contact more or less. And so understanding again the distinction between follicle stimulating and luteinizing hormone, and oh, by the way, another name, and it's confusing. Diabetes means the great thirst. So we spend most of our time in the class on diabetes mellitus, mellitus, which is called sugar diabetes. Many used to call it that. We generically refer to it as diabetes. Diabetes insipidus, insipidus, formerly known as salt diabetes. And the difference, one had sugar, an abundance of sugar in the urine, one had a higher concentration of salt in the urine. Okay. All of those, particularly the distinction, that's why you need to qualify it. So, I mean, in a hospital sense, you say diabetes, everybody knows what you're talking about. And typically the one you specify is diabetes insipidus, and that's the failure to make adequate amounts of antidiuretic hormone. Because if that's there, you're going to be urinating out a whole lot of stuff. Okay. We deal with thyroid hormone, so important. Thyroid impacts every physiological process. I can't even think of the exceptions. So all cells are pretty much stimulated. It basically increases metabolic activity of all cells. If it's not present, then metabolic activity decreases. So it's almost like it's like the idling of your motor. Is it too low? Is it too high? Is it just right? And all of it is about thyroid. It's called T4 and T3 are the active thyroid hormones. They require iodine to be completed. The thyroid stimulating hormone tells the thyroid to make more, and what it does is it makes a globulin, a big amount of protein that's unfinished. Okay, in that protein is this abundance of tyrosine, And this abundance of tyrosine requires iodine to finally formulate the T3 and T4, which are then excreted by the thyroid gland and go all over the body. Very wide range of cells. T4 is not as active as T3, so by metabolically removing that fourth iodine, if you will, it basically gets converted to T3, which is the more active form. But the whole idea of the iodine has to do with why we iodize salt. Okay, so it's not, depending on the area. For years before we iodized salt, people stuff had, because of their diet or limitations, they didn't have enough iodine, and you just need a little smidge of it, really. Okay, you and I get it because just commercially in food products that utilize salt. But what would happen without the iodine present in its ionic form, quote unquote, its salt form, what would happen is that T3 and T4 were not released. The brain kept reading low levels by way of the hypothalamus. Remember, there's an arc between where the blood-brain barrier is weakest, the hypothalamus, then sending signals to the posterior pituitary, then to the anterior pituitary, and finally to the gland. Long story short, it told the gland, make more globulin because we need more thyroid hormone, but without the iodine, it doesn't get released. The thyroid swells immensely. And and at that point, it was called a goiter. And again, there's some others. There's one called Graves' disease and another one called Hashimoto's disease that produce very, very similar things. And even the accumulation of fluid behind the eye, what they call an exophthalmic goiter, not the same thing. The classic goiter has to do with iodine not being available. We don't see it in this country, or we don't see it in countries where they utilize iodized salt. But, obviously, there are areas where we still see it that are there. And it's not hard to treat, but it just needs to be treated because you need, without the thyroid. And understand, if you are hyperthyroid, you get to be, people perspire, there's metabolic activity, there's a lot of secretions, there's a lot of agitation, there's, let's say, large amounts of stomach acid. All of those we think about, they tend to be underweight but very active, very irregular, jumpy. Where hypothyroid, the opposite, very sedentary, dry skin, typically overweight. Sometimes when we see, unfortunately, low levels of this prior to birth, now we begin to see various kinds of mental impairment associated with it. There's all sorts of interesting genetically based syndromes. So if you're interested in, you look up or learn more about. Now we make our way down to ACTH is very specific, going to the adrenal cortical glands. And unfortunately, adrenal cortical is just that. There's not the adrenal medulla, not that misplaced ganglion. So it's targeting three different areas, and it causes increase in production of all three. The outer layer is, and you don't have to know the names of the zones. I'm not going to ask you glomerulata and fasciculata and reticularis and all that stuff. But the outermost zone is aldosterone. Aldosterone is that enormous player that's triggered by that angiotensin, renin-angiotensin aldosterone mechanism we spend a lot of time discussing already, both in this unit and other units and units yet to come when we get to the kidney. Okay. This is like units past, units present, units yet to come. It's sort of Christmas Carol, a la Dickensian. And effectively what it does is basically, and again, collecting mostly in the collecting ducts, sometimes in the distal convoluted tubule, inserting openings, basically transporters that transport actively sodium, and then water follows it. We won't go into it any more than that. You've heard it enough. Okay. And so what's it going to do? It's going to increase sodium retention by the kidney, and water is going to follow it. That's the big player. The next layer, the next deeper layer, involves glucocorticoids. We call aldosterone a mineralocorticoid because it really impacts sodium. The glucocorticoids, very important with regard to stress, maintaining sugar balance or sugar availability during stress, reducing inflammation. There's a variety of roles that these glucocorticoids do. But normally, it's to release under stressful situations, which are many that we don't even know about, and keeping our and maintaining adequate sugar where it needs to go. Suffice it to say, any anti-inflammatory effect is where we use it more clinically. Anything from dose packs for an allergic reaction, or or the hives, let's say, versus in an injectable form. And this is not the same as an anabolic steroid. This is a glucocorticoid. Okay. And this kind of steroid, like we're injecting knees or injecting joints or injecting it generically for systemic control of inflammation, where the innermost layer, that those are androgens. Testosterone-like substances, those are anabolic steroids, as well as testosterone itself. These are mostly testosterone precursors or similar products. It's the only place in a woman where testosterone is produced. And because of the impact that it has on red blood cell count, it explains a little bit along with menstruation why women have lower red blood cell counts. But interesting, this is the area where the laboratories have tinkered with those substances to create a lot of things that were in the illegal or anabolic steroid market. Are we seeing less of it today? I don't know. Maybe it's less discoverable. I mean, as long as HGH and anabolic steroids, I've told you, they're they're wonderful because what they do from its performance enhancing status is they utilize fat. So you get rid of fat, you end up with lean muscle and muscle mass, accelerated bone healing, wound healing, etc. And that's why when they're utilized appropriately, they're important. When they're utilized inappropriately, they create problems. They benefit in the short term, but in the long term, they cause a lot of problems. The excessive amount of fats and the impact of the negative feedback with large amounts of testosterone-like substances can really have an adverse impact on fertility. It can have an adverse impact on skin, on vascular disease, and unfortunately, we see a lot of psychological malfunctions, things like roid rage, that type of thing, which can be a little scary when people, you know, how it directly it impacts anger management, those types of things. I have no way to explain that to you, but just understand that it does. Okay, and again, that renin-angiotensin mechanism. Renin is effectively an endocrine hormone. It's released in the bloodstream directly by the kidneys, and we revisit that again when we look at what's called the juxtaglomerular apparatus. You may remember from anatomy, it's there in the kidney, and it's absolutely significant. So that's renin, and again, angiotensin is effectively another agent, but that's you have to think of that as just a protein that's typically in its inactive stage. It's part of this, and I don't think we're not going to, other than understanding the end product is renin-angiotensin and then aldosterone, and the activities of angiotensin when it's activated into what's called angiotensin 2. Surely its most important action is to cause the aldosterone because we constantly have to keep sodium and retain it. I mean, it's very important. And typically, we don't worry about sodium levels, so there's always a certain degree of activity. And this is one of the many ways that the kidneys demonstrate auto control. They maintain your blood pressure, as we alluded to that in the blood pressure part of the program. But the other three things that it does makes you thirsty, makes sense. It causes antidiuretic hormone, which just retains water, and its name gives it away: angiotensin, tensing or tightening blood vessels. Okay, so we covered that, and then we get to the famously to the pancreas. That's all about diabetes. Insulin and glucagon are produced there. They are it. Okay, those are produced in the islet cells. The pancreas produces a lot of hormones, both endocrine and exocrine. It's a mixed gland, just like the gonads are. Gonads, estrogen and progesterone and testosterone are its endocrine production, but there's a variety of secretions that are exocrine in nature, not the least of which are eggs and sperm, or a variety of digestive chemicals that we'll see when we look at digestive vis-a-vis the pancreas that are there. Glucagon works on the liver, raises blood sugar. Insulin works on all sorts of cells, wide range, where glucagon's a limited range. Okay, and what it and lowers blood sugar. It facilitates the entry into the cell by facilitated diffusion for the purposes of basically utilizing glucose, using the sugar as an energy supply for that myriad of things it does: cell metabolism, healing, repair, normal functions, etc. So, and we're using carbohydrate or sugar effectively as an energy source. The glucagon is more of an emergency source of sugar. Typically, even though they're released frequently at the same time, like I said, there's a balance between them. So we don't get, like I said, living systems don't make sharp turns. And when they start making sharp turns, you look for an underlying fault in either glucagon or insulin, and that's a real tell about somebody being in a pre-diabetic environment. If you remember those utilization curves that I drew up on the board. Other than that, okay, you'll see glucagon playing a role, part of fight or flight. Will certainly be activated then. Anything where we need to basically break apart glycogen, put an additional sugar in an emergency situation, etc. Now we're looking at that kind of a release factor, where we're going to get a real uptick in glucagon, where insulin's relatively constant throughout the time, with tiny amounts of glucagon sometimes to balance it, but the sharp peaks in glucagon, you have to think about fight or flight. So I think that's always significant. And again, the distinction, I'm not going to make the course about diabetology. I mean, depending on where you're going to learn more. Depending on your interest, you're going to learn more. But again, type 1 typically falls with insulin. Autoimmune, now generally accepted to be autoimmune in nature because of the proteinaceous deposits we see critically in organs, mostly the kidney. The wide range effects, that's the predominant theory now. Okay, type 2, a fault in it may be the insulin itself in some way, shape, or form, but typically it's the receptors or the ability of the insulin to enter, to basically activate the cells to utilize sugars. And what we're left with is effectively high blood sugar. And because of the high blood sugar, okay, we see associated problems with excessive sugar and fluid loss in the urine, and all those three polys, because you're polydipsia because it makes you thirsty, polyphagia because you're starved and eating is the way we start to replenish energy, and polyuria because of basically the osmotic effect of the glucose that's spilling. And remember, transport maximums. Now, when diabetics are out of control, inevitably over time, particularly when it's a high number or a higher number than it should be, now we begin to see that effect of the glucose pulling along extra water into the urine, that sort of osmotic effect that's there. And again, we take a look at A1C levels. They're important. They're really important because it's a good measure to see how efficiently in our management of diabetes. But moreover, it's a nice snapshot to see if someone is prone to diabetes. So that's become pretty routine on annual physicals, particularly as people get older. We look for glycosylated hemoglobin. If it's in the normal range, which I think is under 6 or 5.9 or less, it's great. Mine was like that. Very happy. You get to that 6 to 7 range, then your physician's going to tell you about diet, it's going to tell you about exercise, all the do's and don'ts. Look at the family history, and anything over 7, now you're there. Even if your sugars are borderline, basically you're there. But we also utilize that for management purposes. It's become sort of the go-to, other than the glucose tolerance test, which we still utilize depending on if it clarifies the picture, would be the way I would describe it, and really useful for management for those who are into diabetes. Like I said, it's something I worked a lot with. But I think that's all part of it. Don't forget the fatigue issue, because without ATP, you're going to have fatigue. And so all the different problems, the biggest problem is with diabetes is we don't utilize sugars. The next thing metabolically, our bodies will then utilize our fats. And when you're utilizing fats and you're breaking down fats, you're going to get fatty byproducts. Basically, you're going to get what we call keto acids or ketone bodies. Those are basically short chain fatty acids that slam into each other in the bloodstream, in tissue, and they create these what we call keto acids or trans fatty acids, depending on what the really what fats you've ingested. And that's why eating healthy fats is so important, and staying away from things that have all sorts of effectively hydrogenated and partially hydrogenated polyunsaturated fats. Think margarine. Think don't use it. Okay. And so all of those are part of it. So I think you need to understand where all those things coming from. Don't forget the action of erythropoietin. We've discussed that a couple of times vis-a-vis bone, but what that is from the kidney. So damaged kidneys can't necessarily make it, but that's going to stimulate effectively more than anything else, red blood cell formation. We talked about being involved when we did the blood unit and sort of reinforcing it with being at elevation, inappropriate usage like blood doping. I think it's important just to remember about all of those things. Don't forget leptin being produced by fat cells, and we re-explore that when we get into reproductive because it plays such an important role in sexual development and particularly menstruation. Okay, natriuretic peptide A, N is in Nancy, B, where fluid overloads, and it's the anti-aldosterone. They encourage the natriuretic means diuresing or getting rid of sodium and water following it. And it comes from, tiny stretch receptors, just like nitric oxide is in blood vessels with tiny stretch receptors. These tiny stretch receptors in the ANP in the atrial, where the A comes from, are going to basically have the same kind of effect by inserting something into the distal convoluted tubules and the collecting ducts, but in this case, it's going to oppose aldosterone by causing sodium to get into the urine. And the thymus we really will deal with it more. We're just starting immune system. We start getting into T cells, but certainly that's its endocrine role. It does play an impact in the growth and development of white blood cells. I mean, growth is probably the wrong term. Development would be a better term for white blood cells. And then we get more, and now the rest of it is all basically just talking more about the fine points of this and sympathetic nervous system. If you remember fight or flight, you got it covered. Okay. Sympathetic nervous system, that controls blood pressure. The parasympathetic has nothing to do with smooth muscle or blood vessels. Okay. So think about what happens in fight or flight. When it's pure sympathetic, the opposite is parasympathetic. It's the best way to do it. So what happens in sympathetic? Fight or flight, eyes wide open, breathing is rapid, dries up secretion, heart rate increases, force of contraction increases, cardiac output increases, respiration increases, bronchi dilate because you need more air, blood redistributed, opening passageways to the heart and to skeletal muscle where you're going to need it, restricting the blood flow to gastrointestinal and genitourinary structures, maybe sometimes diverting some to the skin for heat dissipation, encouraging, and this is the oddball of that system, encouraging perspiration by the sympathetic. It's the only place where it releases acetylcholine in the postganglionic nervous structure in sweat glands to increase perspiration because perspiration, as it evaporates, cools. Don't forget nicotinics and muscarinics. Remember, it's an odd system. It's just two nerves. And they have ganglia, switching stations, so to speak, or accumulations of synapses of cell bodies outside of the central nervous system. That's why we call them ganglion, not nuclei. And the sympathetic, again, from thoracic nerves and lumbar nerves, and the ganglia are, for the exception of the one in the adrenal medulla, very, very close to the spinal cord. But outside, but again, they're peripheral nerves, and they have long, very, very long postganglionic ones that go all over to a vast amount of structures. We'll go back and look at the diagrams. Whereas the opposite, with long preganglionic and short postganglionic, is the parasympathetic system and all the structures it goes to. And so understand the ones that parasympathetic does not go to blood vessels, number one, therefore kidney would be number two. And effectively, it doesn't really go to the skin if you want to think of it that way. So understand all of those types of things that I've discussed, what the pupils do, what your heart does, what the respiratory passageways do, what the kidneys do, etc., etc. Consistently, acetylcholine is the big player from both preganglionics, sympathetic and parasympathetic. We call those nicotinic receptors because nicotine mimics those effects. Muscarinic receptors are in the postganglionic fibers of the parasympathetic system because muscarine, that mushroom poison, poisonous mushroom extract, mimics it. And then the other ones, the ones that's left, is the postganglionic sympathetic, and we classify those as adrenergic because they release a norepinephrine. And then the only one that's slightly different is the one that's sort of misplaced ganglion that goes directly into the bloodstream rather than to a target organ in the adrenal medulla, which releases both norepinephrine and epinephrine, which are very similar. Subtle differences, but very, very similar. Okay, and then you have to know about what alpha adrenergics and beta adrenergics are, and some examples of the differences in what they do. Things that block it, sympatholytic, things that mimic it, sympathomimetic. Same thing with parasympathetic. Parasympatholytic, block it, which means it acts like a sympathetic. Parasympathomimetic mimics it, so it acts parasympathetic. That will serve you very well if you're going to ever take a course in pharmacology because it's all about that stuff. So be familiar with those types of things as well. Why? I particularly know some examples of beta 1s and beta 2s as much as anything else. All the different parts about that. So the impact of beta 1s on the heart, the impact of the vagus nerve on the heart, because there's some of those oddballs are important, and that's where the vagus nerve comes in on the heart. Whether it's inotropic or chronotropic, we reinforce that in subsequent lectures. All the different things. These are all part of it. Okay. Just about done. I think that covers everything. All right, we're good. If you have any questions, send me the email. I will get this to you today. This is the 18th, so tomorrow, I should have it in your hands by sometime this afternoon on the 18th. So, be in touch. Thank you. Have a great break in the meantime. Bye-bye.